Okay, so in continuing our work with gas laws, now we've done the combined gas law and the ideal gas law. From that, we actually had a scientist start looking at what happens when there's multiple gases. And so Dalton came up with his law of partial pressure. It's a really easy one to understand. Let's go with the basic one I know most of you have already dealt with. Let's say we have a balloon. There's our balloon. And let's say we filled our balloon with helium gas. So it floats. And so really what it has a whole bunch of molecules of helium gas. Now, the process of filling a balloon, as you put that gas in there, those molecules are moving around, they're colliding with each other and the walls of the balloon. And because they're colliding there, they're going to apply a force, expanding the balloon to its size. Now let's say, you know what, you didn't like how big that balloon is, you wanted it bigger, but you ran out of helium. And so instead of adding helium, you add oxygen gas. And so you add oxygen gas, and you'll notice that the balloon will get bigger. And it gets bigger because as you force all of these oxygen molecules in there, they push at each other. There's more things colliding, hitting each other and the walls, and that will cause the balloon to expand to become a bigger shape. Dalton saw this and said, okay, wait a minute. There has to be a total pressure that is equivalent to the walls of the object that it's hitting. If I put another gas in here, let's say I put argon gas in here, the balloon's just going to keep getting bigger. If I keep adding gas, the pressure is going to keep increasing until the balloon pops because you exceeded the elasticity allowability of that wall. And so Dalton said, you know what, this total pressure is actually the addition of all of those gases. So it's equal to the first gas, which in this case we said was helium, plus the pressure of the second gas, oxygen, plus the pressure of any number of gases that you want to add. You can keep adding in. You can find the individual pressures of each of those gases, add them together, you get the total pressure. Cool. Which means if I know how much gas I'm going to add to something, I can get to the pressure itself. So let's look at an example problem of this. Let's say I have a 4-liter container. It's a fixed container, so it's not going to change its volume. And let's say I'm going to add about 8 grams of helium, 32 grams of oxygen, and we should add one more. How about 22 grams of carbon dioxide. Okay, I add all of these to a sealed container. So here's my sealed container. It's not going to change, but I'm going to have all of the gas put in here. It's going to fill the container completely. I would like to know what is the pressure on the walls. Maybe I have a cap that can only take so much pressure. How much pressure does it have? This is what this problem can solve for you. So real simply, I'm going to look at it going, okay, the total pressure here is equal to the pressure of helium plus the pressure of oxygen plus the pressure of carbon dioxide. Okay. And let's say we're at 30 degrees Celsius is the temperature we're adding these together. So I'm going to solve each of these individually using my ideal gas law. Pressure times volume is equal to the moles times the rate constant times the temperature. Okay, so let's solve these up. So let's find the pressure of helium first. The pressure of helium is going to be the number of moles. Number of moles is 8 grams divided by its molecular mass, which in this case is 4 grams per mole. I looked that up on the periodic table. Then times R, which is 0.0821. Times the temperature. Now temperature must be in Kelvin, so real quickly we'll convert that. So 303 K. All over, I'll divide the volume over 4 liters. This will give me my first value. Let's plug in our next values to set everything up. Pressure of oxygen is equal to 32 divided by 32. 32 grams, molecular mass of oxygen is 32, times 0.0821 times 303 equals. And let's do carbon dioxide. Pressure of carbon dioxide is equal to the moles, which is 22 grams. This is 12 plus 32 for 44 grams per mole times 0.0821 times 303. Okay, so I can now solve all of those. Go 3, 4. Okay, so this would give me 6.22. 12.4. 3.1. Okay. These are all my pressures, and since this is pressure, this is atmosphere. Oh, by the way, all of these were divided by 4. Sorry, I left that out. Okay. So the total pressure is equal to 12.4 atmospheres plus 6.22 atmospheres plus 3.1 atmospheres. I'll just leave this at 2. This is your math. Total pressure, according to Dalton, if I add all of these gases, would be 21.788 Ns. Wow, that'd be a lot, but then I put a lot of gas in there. Now there's a couple other shortcuts we could do. If you notice, all of this work right here was the same. So I could have actually added all the moles instead of doing pressure. So you could also, for Dalton's law, go moles total is equal to moles of 1 plus moles of 2 plus moles of n. So in this case, I could have added the moles. So I'll do that real quick. And so the moles total is equal to the moles of helium plus the moles of oxygen plus the moles of carbon dioxide. And the moles was 2 for helium, 1 for oxygen, and 0.5. So the total moles was equal to 3.5. I then could take that and plug that into PV equals nRT. And so so I use total moles, it's going to give me total pressure is equal to 3.5 moles times 0.0821 times the temperature divided by the volume of your container, and you would have got the same answer immediately. It doesn't matter which way you go, both options are viable, and that's Dalton's law. Now, we're going to look at the special case. In most cases, when we do lab work and we try to collect gases, the pressure that we care about is going to be the water pressure. You collect most gases over water, and we can't stop water from becoming vapor. It's very volatile. Volatile means evaporates and changes state very easily. So on most problems, you are going to be looking for the pressure of water with the key statement, hey, this was collected over water, which means there's water pressure as part of Dalton's law that we'd have to account for. And we'll do that next. Good luck.